All right, so we're going to do this order of operations problem. But before that, let's talk about the order of operations, perhaps ad nauseum. It's good to talk about. Let me ask you this question. If you did not have an agreed upon order of operations, how would you know what order you're supposed to do things in? Lots and lots of parentheses, right? In fact, in parentheses around every pair of numbers, right? Because that is what plus does. It puts two numbers and makes them into one number. So if I want you to know which pair to do what to, I have to use parentheses, unless we have an agreed upon order of operations, right? So this is what math would look like without an order of operations. It's kind of cluttered, right? And the only reason we have an order of operations is to make math less cluttered, right? Just saves us parentheses, saves us on our pen budget, right? Because we don't have to spend so much on pens because we're not writing as many parentheses. Have some walking around money, so you can thank the order of operations for a little extra cash in your pocket, okay? If we do have this order of operations that we've agreed upon, look at parentheses. That's kind of a silly thing to even include these. Of course, parentheses trumps everything else. That's what parentheses are for. They group things together. It's just natural. Okay. Then we agree that with exponents would come next. There's no exponents here. Okay. So then we work our way down to the multiplication division arena. All right, level of order of operations. So here we see some multiplication. All right. The reason there are parentheses here is that without order of operations, it's to tell us to do this multiplication before we do something like, say, subtract a number from 5, right? The order of operations already tells us that that's the agreement. Okay, I'll use the word agreement a lot until you're sick of hearing the word agreement, because that's what the order of operations is. So we don't need these parentheses, because the agreement, the order of operations, is that we'll do that multiplication before we do something that's below multiplication, like addition and subtraction. And again, these parentheses are here to tell you to do 18 divided by 3 before you subtract, say, 18 from something else. Right? This 18 is not going to be part of subtraction. It's part of this division, because that's the order of operations that we agreed to. So we don't need this parentheses because we agreed to do division before we do subtraction. Let's keep working our way out to the next largest set of parentheses. That'd be this guy right here. So this one is telling us to take this number, since we've already agreed to do multiplication and division first. It's saying to take these two numbers and subtract this number from that number, and then to add 3. Right? That's what that parentheses is telling us. Do this first and then add 3. Does it matter if I do this first and then add 3? Or could I just do 3 plus this minus that, and then would that be the same thing? It would not be the same thing. Let's take a simpler example. Okay? So what we're going to talk about here is called the associative property of addition. And so first, let's just recognize this is addition of the negative, whatever that number is, right? -6. So it's addition of -6. So I'm just going to make up some numbers. Let's say I take 5 plus 7 minus 11. Okay. So to make it like this one, we would do this first, and then we would do plus 5. And then I'm going to ask you, isn't that the same as if we did 5 plus 7 and then subtract 11? Let's find out. We'll use a number line. Number lines are great. Okay. So here's 0. We'll do it with the parentheses around that first. Right? Which addition or subtraction we do first is the associative property. 1, 2, 3, 4, 5, 6, 7. We start at 7. We're going to subtract 11, right? So we're going to go back 7, 8, 9, 10, 11. So that's going to take us to -4. Right? That's the first thing we're doing. 7, go back 11. So that's done. That's where we are. We're at -4 now. Now we're going to add 5, and we wind up at 1. Let's see if it's any different if we start at 5, go up 7, and come back 11. You decided, in your heads right now. Make your bets. Instead of doing that, we'll just work it from left to right. 5 plus 7 minus 11. I'll do that in red so that we can distinguish. So 5, 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5, yeah. So start at 5, go up 7. So 1, 2, 3, 4, 5, 6, 7. So we add 7, 5 plus 7. And now we're going to come back 11. Let's see if there's any difference. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We wound up in the same place. That was my question. If we do the subtraction here first and then we add 5, is that any different than 5 to 7 minus 11? It's not any different. And it doesn't matter how many numbers there are, if they're positive or if they're negative, as long as we treat this as not just subtraction, but the sign of this number, and the sign follows this number around no matter where it goes. Adding negative 11. It doesn't matter what order we do that in. That's called the associative property. And if we start moving numbers around, that would be called the commutative property of addition. So, all that is to say, we don't really need these parentheses. It doesn't make a difference if we do that first, or if we do this first. This first, or this first, it doesn't make a difference. Okay? And now if you look at like the whole thing as a whole, what we have here is a number that we agree to do first, a number here that we agree to find first, and then adding and adding and adding and adding. This is kind of the same kind of an argument we just made here. It doesn't matter what order we add things. As long as it's all addition, and think about subtraction as addition of negative numbers, it does not matter the order we do them in. Whether I add these two together and get 3, and then add these together and get whatever number that is, and then add those two numbers together, it doesn't make a difference if I do that or if I just do 1 plus 2, and then I add 3 to that, and then I add 20 to that, and then I subtract 6 from that. It's all the same. And we don't need parentheses around the entire expression either. So what has the order of operations done for us? Erase the parentheses. Now we can't get rid of parentheses altogether. Sometimes I want you to do things in a particular order that if you were just doing the order of operations, it wouldn't work. It wouldn't work out the way you wanted to. So we need parentheses to kind of trump the order of operations from time to time. All right? And we can, even with the order of operations, we can overuse parentheses. It'd still come out the same, just be a little bit redundant with all those parentheses. Okay? So just a reminder that we're going to use this agreement. Sure, it can be that big. E, S. And, you know, I never think of PEMDAS. I don't really remember, please excuse my dear Aunt Sally, it doesn't come to my mind when I'm doing math. I think just because I've been practicing it for so long that it's just natural, it almost seems like the right thing to do, even though it's not the right way, and the other way is the wrong way. But also it kind of makes sense that like addition and subtraction are like not that big a deal. Like numbers don't get big very quickly when you add them. Not as big as when you multiply them, right? It's almost like this is more powerful than addition and subtraction. Multiplication and division change numbers more greatly than addition and subtraction. Exponents, even bigger deal. I guess repeated multiplication. Like 2 times 3 is not as big as 2 to the 3rd power, right? So that's like even bigger deal. And then parentheses, like that's just obvious, of course. Parentheses trumps every other order. We group things together with parentheses. Or you can remember, please excuse my dear Aunt Sally, the point here is that we do multiplication and division. Why are they together here? From left to right. Even if division, even though this is on the right of M here, if you see division before multiplication, do the division first, before on the left. Okay. So let's jump over here, and we'll work this using that agreement. Okay. So let's take a look at the parentheses. Let's think about the order of operations. I guess we should do this parentheses first, right? Because if I try to do these parentheses, I wind up needing to do these parentheses first. So let's work on that. 3 times 3. We got 7. Into those parentheses, we're dividing by 4. Yes, it is. Can I just do 7 times 2?
Yeah.
If you think no, and if you think no because we haven't finished with the parentheses, well, that's not really a problem. Because this is just going to be some number, right, when we get all done. And by the order of operations, we're not going to add this number to 2, right? No matter what happens with the parentheses get done, that 2 is going to get multiplied by that 7, because multiplication happens before whatever's next, which is addition. Right? So we're going to wind up multiplying those together anyway. So we can do that at the same time. around these parentheses here. We got 7 plus 9, right? Rather than 10 times 3. Right? I'm going to try to do 7 plus 3 first and then multiply by 3. But you wouldn't do that because multiplication becomes just the agreement. It's not right and wrong. It's just agreement or not agreement. We've agreed to multiply first before we add. So we'll multiply the 3's together. And we've got divide by 4 times 2. How about 4 times? Should I do the 4 times 2 in this next step? Why not? Division. There's a division to the left of this multiplication, so we should do the division first. So we've got 7 plus 9, so that's 16. Divided by 4 times 2, so we're going to take 7. We're not going to do 14 plus 16, right? Because we would do division before that. 16 divided by 4 is 4 times 2. 14 plus 4 times 2, not 14 plus 4, because multiplication comes first. So we do 4 times 2 is 8. It's 14, and we have 22. Is that helpful? Mm-hmm. Hopefully you did it right. If you didn't, the best thing that could happen is you learn something. You learned what your mistake was, and that's, well, to me that's better than just having done it right. It's good to learn, and learning is the fun part. All right, other questions? Let me go back to the homework screen. Any questions from any other part?
Number 4, where we simplify the radical expression.
This one?
Yeah.
Okay. So I'm going to highly recommend, I can't force you to do this, but I'm going to highly recommend that you ask yourself, what do I feel like can cancel? That's the first thing you're going to ask yourself. What does it feel like can cancel here? Yes?
The 2 x's behind the 2, like the x on the bottom with the one of the x's behind the 2.
So this and just like one of those? Okay, so here's the, if you think that an x can cancel, I just want you to answer that question. Don't worry about right now how to cancel it, like what it'll look like afterwards. Just ask yourself, what do I feel like can cancel? The answer is x, right? Okay, so let's, to make sure we don't make any mistakes, let's just say we want to cancel an x. If we can cancel an x, it will be a common factor, right? It will be a common factor. That's important. Okay? So what you did right there, you weren't treating it like a factor. Okay? At least not a factor of the numerator. So if we can cancel it out, it has to be possible. It's not to say we have to do all this work every time, but it does have to be possible to write it like this. X over x times some other fraction. And then we can multiply straight across and get this fraction back. Okay. So in the denominator, let's do that. That'll be easy. X times what gives me x? 1. All right. Now we're going to have to multiply x by this numerator, keeping in mind that to get several terms, we're going to have to distribute. Right? So we're going to have to set that up. What do we distribute it to get 2x squared? 2x. Now, this is the part that we always forget about when we actually want to simplify a rational expression. We have to multiply x by what to get x? A negative 1, minus 1 there. Now we've set it up so that it does multiply back to this fraction. We do get that back when we multiply these together. And that, since that's the case, now we have x divided by x is 1. Anything divided by itself is 1. So now we have 2x minus 1 over 1, or 2x minus 1. Technically, what you wanted me to do is cross this out and cross one of those out, but maybe I didn't give you a chance to get to it, but you didn't mention anything about this x. Right? So we've got to ask ourselves, is it a factor, not just of something in the numerator, but the entire numerator? Okay? And when we say factor, we mean it's possible to take that factor that we want to cancel out and multiply it by something else and get the original expression back. And I know that sounds like a mouthful, but you can't define factor any faster than that. Right? And what I'm essentially saying is that 3 is a factor of 15. It is a factor of 15. I know that it is because I can multiply it by 5 and get 15. I can multiply it by something else and get 15. Well, x is a factor of 2x squared minus x because I could multiply it by something and get 2x squared minus x. Right? You gotta think that way. If you're not thinking that way, you're gonna make a lot of mistakes. And as we do this more and more and more and more, and we get used to it, it'll become more like muscle memory, and we won't feel like we need to do that process. But if you are making mistakes, if you are canceling an x here with that one, and not even considering that there's another x over here, do this for, the next 20 problems that you do that are like this, and don't make any mistakes, and then try and shorten the amount of work you show. Any other questions? Should I go back and let you look at it? So as soon as you get to the point where nobody asks any questions, what everybody's saying at that point is, I'm ready to show off my abilities. I feel confident I can do any of these by myself without any assistance, and I'm ready to show you that. Yeah.
How would you do like number 2, the second?
This one?
No.
Oh, a different one. This one?
Yeah.
This one. We're gonna talk about this. Let's talk about it right now. Go over here. In short, you would take this and distribute it to every term in the parentheses. Right, what you get. Do that. So, what's 2x times x squared? 2x cubed, because let's look at 2x times x squared. That's just 2x times x times x. That's 3 x's we're multiplying together. To shorten that up, we just use a power of 3. And 2x times negative 9x, that would be what? B minus 18, what? Squared. Yeah, so we got a negative 2x times 9x. Right, so we can just put the 2 times the 9 and then times the 2 x's. So we have an 18. X times the next x is x squared. Right. So now I'll leave the explanation for after because it'll be fine. If you can do that, distributive, you can accomplish what I want you to accomplish. We're going to talk about the distributive property today as part of class. Are there any other questions for the homework? Does that make sense, Darren? And if you feel confident, you're ready to show off, then pass your papers into your left. Collect those. Okay, so we'll start with this guy. Let's start by asking ourselves, what do you think might cancel out between the numerator and denominator? And x. Let's try x. If it's possible, just like we talked about from the homework, it has to be possible to write it as the factor you want to cancel out over itself times some other fraction. That would eventually be your simpler fraction. If it's not possible to write it this way, then it's not possible to simplify this fraction, or you've picked the factor incorrectly. Right? So let's start across the denominator. X times what gives us x squared? X. Let's go across the numerator. We've got to distribute it to some stuff. So x times what gives us x squared? That's x. We just did that. X times what will give us the 4x? Well, that's great. Looking good. Plus something that we can multiply x by to get 1. 1x? 1, yeah, okay, so 1 over x is the only possibility, but the problem with that is what? Is what? Yeah, you got a fraction inside a fraction. When I say simplify, would this qualify as? No, it's different, right? It's differenter, but it's not simpler. It needs to be simpler. And to plug something in for x in this guy would be much more complicated than in this one. So, Cindy's right. that is the way you could do it, but then it's just not simpler. So we would say, we would reject that possibility. And what other ideas, I mean, can we cancel it 2, do you think, or an x squared? Is there any other possibilities? No. No, it's not possible. Yes?
That's a great, you just want us to put the number they got right by as a question.
Well, what would be helpful if you want to know, it would be on the left of the, like in the left-hand column, just put, 2 out of 5, 3 out of 5, 4 out of 5, whatever it is. Right? And it's kind of a judgment call on your part, especially trying to decide between a 1 and a 2 and a 3 and a 4. It's a little bit of a judgment call there. I will be going over this myself because, like I said, I want to use it as an opportunity to see how you're doing, if you can do it correctly. On your own, without assistance, do you understand the concepts? So I'll be going over it. I'll be scoring it as well. So if you feel like the person grading is being unfair, don't worry. I will be grading him as well. All right. But this way, we get to see some marks on our paper and understand what we did right and wrong right away. And then by the next class, I'll have them back to you as well for you to keep. Okay? So how about this one? We have to start with what we think will cancel. A 3. You think a 3x. So if it's possible, then we should be able to write 3x over 3x times some other fraction and get the original fraction. Started on the denominator, what do we have to multiply 3x by to get 9x? 3. 3, good. 3x times 3 is 9x. 3x times what will give us 3x squared? Okay, 3 times x is 3x squared, just double checking, looks good. What do I have to multiply 3x by to get 12x? 4. 4. Okay, you want to double check? Because, when you write that down, your heart starts skipping a beat, you feel like you did it, and you're successful, and you're winning. I just want to make sure that it does work out, that it does distribute correctly, it does work out. Now 3x divided by 3x is 1. So now we have 1 times this. So this is equivalent to that. This is the same as that. Okay. Am I really a great explainer? Do you understand it? Did I do well? Or do you have any questions? Okay. All right, on to this guy right here. I'm just going to write the correct answer, and if you're confused by that, we'll talk about it. This means to multiply something by itself 4 times, so 4 x's. Any controversy over that? Pretty confident there are some incorrect answers out there. If you see it's incorrect and now you realize, like, oh, I see what the mistake is, great. But if you're still like, I think it should be this, are you sure?
And number 2, it's like,
For this one?
yeah.
Uh-huh.
They did it right, I think, in like the way that they were, I know what they were trying to do.
Right.
I'm not sure if it's a 3 or a 4
Oh,
because
okay.
they did X instead of.
Oh, well, they could have gone
They
a
knew.
little farther.
I know they knew,
Mhm.
but they just.
Maybe pointed out, said like maybe could have taken a 3 out. I think that's
Okay. I just put 3 in.
no halves. I don't deal in halves. That's why I have a 0 to 5 scale. Okay. So are we good on this, or is it just no questions at all? Nobody feels like it should be like 5x and 5x and 5x and 5x and 5x? Nobody thinks there should be a negative on all of these terms? All good. Right. The most basic math class answer would be the order of operations. Exponents come before multiplication. Right? This is multiplication by -5. This is an exponent for x. So we do the exponent first and then multiply by -5. That's what the exponent was telling us to do, to multiply x by itself 4 times. So if we're good on that, then great. So I'm going to take to the next page. So it's easy. So we worked an example from the homework, from the inside of the parentheses out, and we do multiplication, division, what's the order? So we'll get going on this. Let's say way. Here's the innermost parentheses. We should definitely start there. So we should do what inside this parentheses?
3 times 2.
3 times 2, multiplication first. We got the 6 there, and 4, okay. Well, I can't add the 1 until I multiply by -7. I can't do that until I add these together, so I can't do anything there. Okay. I can't divide by 8 until I know what this number is. Okay, so I can't do anything about that. Should I multiply by 4? Should I just erase that and multiply? Why not? You got the division first, right? The 8 belongs to this division problem, I guess, before we multiply by 4. So we can't divide by 8 until we know what this is. How about -6 times 3? Can we do -6 times 3? We can, in case you're wondering. Can do that. Because this is just negative, well, it's 2 minus 6 times 3, which is really plus this. Multiplication comes before addition. Okay? So it's this -6 times 3. And this 3 is next to, it is multiplication by this guy here, but this is just going to be some number when we get all done. And we're going to have -6 times 3 times some number, and we'll just multiply from left to right. So, do -6 times 3, that'll be completely acceptable by the order of operations. All right, then we move on. Let's look at the innermost parentheses. Always go for that. We got 10 inside there. -7 plus 1 divided by 8. 7. Let's see. Still, there's just really nothing I can do. It's like whittle down these parentheses. 5 minus 7. Should we do that?
No.
Why?
Times.
You gotta do the multiplication first, right? M dot multiplication before addition or subtraction or whatever. So we've got 5 minus 70 plus 1. 8 times 4. Still can't do any of these things yet until we get the parentheses taken care of. Alright. So now we can do like 5 plus 1, right? Get 6 and then subtract 70. It's called the commutative property. We can move this 1 over with this 5 since it's just addition and subtraction. 5 plus 1 is 6 minus 70. What's 6 minus 70? And it's negative, right? -64. Divided by 8. Then multiply by 4. Then add 7. Okay, so then we're taking a look. We're looking at what do we do next. What's the first thing that we're going to do? Multiply that -18 by -64 because it's multiplication comes before everything else. Division and multiplication come at the same time from left to right. 2. What's -18 times -64? So it's going to be positive, right? Now we just have to figure out what 16 times, or 18 times 64 is. Good. Divide by 8 times 4 plus 7. Do division first. I think that was 144. Done this a few times. This is the 3rd time I'm doing this problem. Okay, so what's 144 times 4? 5, 20, 7. Add 3 numbers together. Where are we at? 585. There we go. Good. Any questions? Hand it back to the person it came from. So express it a different way. We're, instead of adding 3 and 4, we're using what here? Distribution. Use the distributive property, right? And while you might know how to use a distributive property, understanding the distributive property will save us some mistakes in the future, or at least an easy way for me to explain what your mistake is, okay? So while you may never make distribution mistakes right now, there's going to be something in the future called multiplying polynomials by other polynomials. You've done that before, I'm sure, in algebra, right? You multiply a polynomial by a polynomial. You might have even done some of that in geometry. And if we just do it by rote memorization, we will likely make lots of mistakes. But if we understand what distribution is, why it is, then I have at least a tool that we can call back on, and I can help explain this more complicated distribution to you. We should all have some notes ready. This is class now. We are moving along. We're going to start with PEMDAS, but we already had that discussion. And I want you to be able to answer these questions or respond to these things when we get towards the end of class. Think about that. So we use distribution when we multiply something by parentheses. So to start with, let's talk about multiplication and how I can draw a picture of multiplication. I'm going to use a rectangle. Just with a rectangle, I can show you a picture of multiplication. Can anybody think, what about this rectangle could display multiplication to us? Well, like this rectangle has certain properties, right? It has side lengths are a certain size and has right angles and things like that. It has, you can measure all the way around it. You can see how big it is. Anybody think of what property of this rectangle displays the multiplication of two numbers?
Area?
The area. Exactly. Very good. Very good. So I'll just pick two numbers like 3 and 5. Okay. That side's 3. This side I'll try to make look like 5. That side's 3, and that side is 5. The area is the product of 3 and 5. The area. And as I draw this out, we'll see also 5 groups of 3, which is another way that we think of multiplication, right? We got this group of 3 right here. That's how many squares, how many area units run along this side. And I have another one, and another one, 4 groups of 3, 5 groups of 3. So in the rectangle, we have the product of two numbers. Starting off easy here. Now let's see how we can, just in numbers, just like this example, see this distribution. So let's do like, so this is going to be like the length, this is going to be like the width of the rectangle. So let's draw a rectangle. This side I'll make the 5. That's 5. And this side just needs to be 3 plus 4, right? Which is actually 7. But I can also write it as 3 plus 4 and use it to show you distribution. So 3, half part is 3. And this side will be a tremendously large 4. Is that okay that my scale is off? Is that confusing anybody? That's all right? Okay. So we have on this side 5, and on this side 4 plus 3. Right? Or 3 plus 4, doesn't it? So what will the product of this look like? One way to do it is to add these together, have 7 on this side and multiply by 5. But now let's see why we have to take the 5 and distribute it to the 3 and to the 4. Because if I want to find the area of this rectangle, part of that is going to be this rectangle, and the other part will be this other rectangle. So this rectangle is, well, we already saw it here, right? This side is 5, and I need 3 groups of 5. 1, 2, 3 groups of 5. So part of this product is the 3 times 5. Okay. To get the area of this, I also have to consider this rectangle. The area of this rectangle is 5 times 4. So here we have the 5 times 3, and here we have 5 times 4. And how do we get the total area with those two amounts? And you add them together. That's why we add these two things together when we've distributed. So we have 5 times 4 plus 5 times 3, 20 plus 15, 35. Same thing as the other. And here's the last thing that I'll show you about distribution today. That's when we have an x in there, which is one that's more relevant to an algebra class is when we have x's in there. So let's look at like 4 times x. But I'm going to write it kind of backwards, like a 2 plus x. See, now in this case, I don't have the option of adding 2 and x. The x is an unknown quantity. So I can't just add them together and get 7 and then multiply by 4. It doesn't work. So I have to use the distributive property, but the rectangle will help us see that. So first, let's start with this side of 4. Then we need this side to be 2 plus x. So let's look at the 2 part. That's 1, 2. There we go. Now the rest of this is an unknown quantity x. And I could have drawn it really small. Right? I could have cut the rectangle off here. Could have drawn it the way I did. I could have kept drawing this side until I got into the parking lot and then ended it over there. Right? Like the length of this thing is supposed to represent x. But it could be any length. So don't get like hung up on trying to measure this length and figure out how long it is. You shouldn't be able to really measure it. Right? You just have to stop drawing that side at some point. So we kind of have to use our imaginations that this length represents any length. Any length. So this much is 2. This much is x. This whole side is whatever x is plus 2. Right? 2 plus whatever x is. Does that make sense, how that side is 2 plus x? Okay, good. Now, 4 times 2, that's this part of the rectangle. That's an 8. What's the area of this part of the rectangle? But we can kind of say it in a way that's like, well, once you find out what x is, plug it into this expression. 4 times x. 4 times whatever x is. So there's your 4x. So here we have 4 times 2 plus, right, that's the area of that one, plus the area of this one is 4x. So we have 8 plus 4x. And then we can throw x's in there, and we'll get square x's, and we'll leave that particular thing for another day. I just want you to see this picture now, so I can call it back later on. So multiplication as the area of a rectangle, very helpful tool when looking at polynomials multiplied by other polynomials. Okay. Any questions about that? Because I'm about to just close the book on that little illustration and move on to something else. All right. Let's talk about algebra. Why does algebra get the special name algebra? What makes it algebra and not something else? You got it. First, try its variables. And how do we represent variables? With letters. Now, we can do this representing variables in other ways. I have, in fact, a book right here. Right here, which is way over 100 years old. Not the printing of it, but the actual content is over 100 years old. It's in what we call public domain. So Barnes & Noble can print it for free. Like, they don't have to pay anybody to use the material. It's called The Elements. It's the first geometry book ever. And Euclid, the guy who supposedly wrote this, if he in fact ever even was a person, used like pictures like these. And the length of a side was a variable. He even used geometry to prove that there are an infinite number of primes. What's that?
You've read the whole thing?
No. You can see that the stickies are in this chapter and way back in this chapter, because that's all I was assigned in class. And then other people got to explain their chapters to the rest of the class. So it's unique to algebra to use numbers to represent letters. Sorry, I get that backwards a lot. Letters to represent numbers. Okay. And I found a little TED talk I think is interesting. So I'm going to watch it here. Back.
I have the answer to a question that we've all asked. The question is, why is it that the letter X represents the unknown? Now, I know we learned that in math class, but now it's everywhere in the culture. The X Prize, the X Files, Project X, TEDx. Where'd that come from? About 6 years ago, I decided that I would learn Arabic, which turns out to be a supremely logical language. To write a word or a phrase or a sentence in Arabic is like crafting an equation because every part is extremely precise and carries a lot of information. That's one of the reasons so much of what we've come to think of as Western science and mathematics and engineering was really worked out in the first few centuries of the Common Era by the Persians and the Arabs and the Turks. This includes the little system in Arabic called Algebra, and Algebra roughly translates to the system for reconciling disparate parts. Algebra finally came into English as algebra. One example among many. The Arabic texts containing this mathematical wisdom finally made their way to Europe, which is to say Spain, in the 11th and 12th century. And when they arrived, there was tremendous interest in translating this wisdom into a European language. But there were problems. One problem is there are some sounds in Arabic that just don't make it through a European voice box without lots of practice. Trust me on that one. Also, those very sounds tend not to be represented by the characters that are available in European languages. Here's one of the culprits. This is the letter sheen, and it makes the sound we think of as sh. Sh. It's also the very first letter of the word shay'un, which means something, just like the English word something, some undefined, unknown thing. Now in Arabic, we can make this definite by adding the definite article al. So this is al-shay'un, the unknown thing. And this is a word that appears throughout early mathematics, such as this 10th century derivation of proofs. The problem for the medieval Spanish scholars who were tasked with translating this material is that the letter sheen and the word shay'un can't be rendered into Spanish because Spanish doesn't have that sh, that sh sound. So by convention, they created a rule in which they borrowed the ck sound, the k sound, from the classical Greek in the form of the letter chi. Later, when this material was translated into a common European language, which is to say Latin, they simply replaced the Greek chi with the Latin x. And once that happened, once this material was in Latin, it formed the basis for mathematics textbooks for almost 600 years. But now we have the answer to our question. Why is it that x is the unknown? X is the unknown because you can't say sh in Spanish. And I thought that was worth sharing.
It's the reason why we use X so much. So that's what makes algebra algebra. We use X or A or B or M or whatever we want to represent some number that we don't know. Okay? So as part of your homework, I want you to be able to write some simple algebraic expressions. Okay? So try this one. Let's do 4 less than a number. If I said 4 less than 12, what would I do to figure that out? That's 4. If I said 4 less than 30, what would I do to figure that out, to find the answer? Okay, so if I say 4 less than, what does that mean I'm doing to whatever number I'm talking about? Subtracting. Subtracting 4 from that number. How do I represent some number? X, A, M, B, N, not O. O is not a very good choice. It's like a 0. Alright, so we don't want to do that. Lowercase l, probably not a good idea. If we do use L, we probably would go like that, right, as the script, so that it's not confused with the number So we choose a letter, we call it, that's the number, and then we do whatever to it the situation calls for. Okay? Let's say that I use an English sentence like, I am 4 times as old as my brother. What is the thing that you don't know? What's the unknown quantity? The brother's age, really, right? Once I know my brother's age, I know my age. Okay, so let's use an algebraic expression to express this. Looks like it's going well. If I tell you that my brother is 12, we multiply 12 by 4, and you would get my age. If I told you my brother was 7, you multiply 7 by 4, and you get my age, right? So 4 times whatever the number is. We can let it be x, we can let it be b. Why might I choose b? It's my brother starts with b. So whatever we want, right? These are all examples of the wrestling of getting ready to leave. Let's not get ready to leave yet. These are all, I guess these two are examples of algebraic expressions. An expression is just a string of numbers with addition and subtraction and whatever other operations you want to use. That's called an expression. When we throw an equal sign in, then it becomes an equation. Okay, so this is not an equation. This thing that we did for the quiz, this thing here, not an equation, right? Just an expression. Really long expression, but it's just an expression. Okay, and these are expressions too. Anytime I write one of these expressions with variables in it, it becomes an algebraic expression. All right. So, an algebraic expression is just one that uses algebra to write an expression. We use letters to represent numbers in an expression. Next, let's talk about the different parts of an algebraic expression. Okay. So this doesn't have any really meaning. It doesn't represent any real life situation that we're privy to. It's just an algebraic expression. Let's talk about the different parts. About that guy, and that guy, like this one, and about, I should circle the negative, this one here. What are those things called? We're called what? Factors? I guess you're right. They're factors, like 2 is a factor of this term. But they have a special name within algebraic expressions. Coefficients. Coefficients. The number that is multiplied by a variable is called a coefficient. And of course the x squared and the x are variables. What is this? And this called? Like an algebraic expression? And also this guy here. Yes, they're all the terms of the expression. Right, and so we get into things like terms and unlike terms. When we say term, we mean basically a thing that is like the product of stuff. If you see a bunch of stuff multiplied or even divided, since multiplication and division happen before addition and subtraction, those things group together to make terms. Okay. So, can I add 4x plus 2x squared? Okay. Let me even back up. Can I add 4x and 2x?
Yes.
Is 4x plus 2x 6x squared?
No.
You think I see this a lot?
Yeah.
I do. Okay. Why do I see it? Because the person doing it is maybe being a little absent-minded, but ultimately not asking themselves, what does x squared even mean? What does x squared mean? X times x. Is any part of this telling me that x gets multiplied by an x? No. So definitely be careful there. But is it 6x?
Yes.
Yeah. I mean, really, what does 4x mean?
4 times x.
Yeah? And that's really the short form of addition, right? 4x means x plus x plus x plus x plus x plus x. And so how many x's are we adding? 6. So short form of that would be 6 times x. What happens when I have 4x plus 2x squared? Why not?
X times x, then you can't add.
Right. Just think about this simpler question. X plus x squared. Is there some way to add them together? This is x. This is x times x. If I try and add these together, there's just no crossover there, right? I can maybe rewrite this expression in different ways, but I cannot put them together into one term. I can't do that. Okay? So likewise, I can't add 4x plus 2x squared. And what I would like you to have, at the very least, is a notion that if I try to add 4x plus 2x squared, a notion that x and x squared are completely different kinds of things. Just like going back to when we talked about adding fractions, fifths and thirds are different things. What makes them different? What makes a fifth different from a third? The size of the piece of the whole, right? So they're different. They can't possibly go together as apples and oranges. These are likewise apples and oranges, right? If this is x, this is x times itself. If this is a meter, this is meter squared. Is a meter the same thing as a square meter? Not, no. I can't take one meter stick and add it to a square meter and get 2, no. It just does not translate, okay? So they are completely different worlds. You cannot add them together. They're not what we now call like terms. They're not like terms because they're a different kind of thing. And if I had 7x cubed, if this is a meter stick, this is a square meter, right? This is meter squared, like an area. What would meter cubed look like? It gives a third dimension, right? Here we get 1 dimension, 2 dimensions. A third dimension would mean that x cubed is like a box, right? Like a volume. Completely different dimensions, literally different dimensions. And so you can't add them together. All right. Of course, you can multiply them together though. X times x squared. That's x to the third. This is x times x times x. That's 3x's multiplied together. Okay. And so yeah, I'm gonna send out your homework. If you don't mind, I had a little discussion with a student yesterday that they were confused about this. If you want like a physical piece of paper with your homework written on it, so that you can like put it in your planner or whatever, then I would be happy to print that out for you. Okay? But you don't have to get that from me like now at the end of class or after school, because I might be changing your homework. That's the idea behind it. Yeah.
So, what's the phone number thing?